Welcome to another RDWorks Learning Lab. Today we're going to carry on investigating this very narrow beam that I've developed on the RF machine. Now, the fact that it's developed on the RF machine makes it no different to the CO2 laser beam that's in this machine here. But there is a big difference in the beam diameter itself when it hits the lens. And that's what I'm trying to investigate. Now, these are raw beams for comparison from the two machines. Now, this one here is the raw beam after mirror 3, which is the beam that's going to hit the lens. And I've got exactly the same situation here from the RF machine. So the difference in this is that this beam is about 3mm diameter. This beam here is about 7 or 8mm diameter. Well, this is 8mm diameter with a 70-watt tube. And this is 3mm diameter with a 30-watt tube. And as you can see, the 30-watt tube has done just as much damage as the 70-watt tube. So in terms of intensity, which is the point that I keep making, the intensity is the thing that does damage, not power. Because of the way in which I've created the beam on the RF machine, it isn't a uniform beam. And so consequently, I can move this test from the centre of the machine, where I generated this, and I've got my smallest beam, to the top corner of the machine, where the beam is a lot bigger. And the beam is around about 6mm diameter here. And you can see, look, changing from 3mm to 6mm has caused this massive difference in intensity. And the different intensity has caused less damage. Now, I had trouble trying to explain this to a couple of people that contacted me. And I had to think of some very simple analogy as to why this would be different to this, because they're both the same power. What I've got here in the background will explain the difference between these two burns here. Remember, these were both 30 watts. The only difference between them is the beam diameter. So what we've got here is the thin beam with an intensity of this much. Now remember, intensity is the thing that does the damage. So we've got a lot of intensity here. In a fixed period of time, we managed to burn this deep with this beam. And in the same fixed period of time, we were only able to burn that deep with this beam. But look, what's in here is 30 watts of brown stuff. So if I change the size of the beam, look what's happened to the intensity. And that, I hope, explains the difference between these two burns. This one is low intensity because it's a bigger beam. This one's the same power but squashed into a much smaller beam. So I get a much higher intensity. And I keep stressing that word intensity because that's the thing that you can see as doing damage. Okay, now today we're going to do quite a few comparison tests for those theorists that want to try and analyse the results that I'm getting. Now, the first thing that I'm going to do is to verify that we've got our beam passing right down the axis of the lens tube, i.e. it's passing properly through the axis of the lens. So we'll just do a quick test here, and I think that's reasonably close to centre. We'll now pop it down to the bottom there, and we'll check how concentric the burn is. I think you can probably believe that that is reasonably true, and that we are passing the beam right through the central axis of the lens. Okay, so I've got a 2.5 inch 63.5 focal length gallium arsenide lens in here, and it's a meniscus lens, and at the moment I've got it set up to 20, 40 plus 8, so 48mm, plus the 10.5 which is buried up inside the nozzle. That's 58.5. Let's take a look along the back here at what size dot we can produce with a 58.5. Okay, so let's raise it now to 59.5. Now we go to 60.5, 63.5. Now, without going to my microscope for very accurate measurement, I've got a little measuring piece of kit here which gets me down to certainly the nearest 0.1, and I could probably get to 0.05. So let's just measure the size of those dots. Well, I've got two numbers on my chart here. One of them is the size of the hole that burnt right through the middle of the card, and then what we've got here is roughly the diameter of the scorch mark around the outside of the central hole. So the smallest hole that we were able to produce was at 59.5, which is 0.3, but it had a 0.1 halo round the outside, and all of these had anything between 0.05 and 0.1 halo round the outside. The smallest possible dot was at 59.5, so that's 4 millimeters below the nominal manufacturer's focal point, and that's with a standard machine with about an 8mm or 9mm diameter beam. Well, I apologise for the jet engine noise on this machine, but it is what it is. I can't change that. The best focal point we found on the other machine was 59.5. So we're going to start this off using exactly the same pile of blocks and beam and set it up exactly the same, 59.5. I've got the same 50 millisecond pulse set on this machine. So, direct comparison. This one is set to 100% at 30 watts. The other one was set at 70 watts. This is using half the watts in the same time. Well, I've now turned the lens over and we've got it meniscus side up. We're going to repeat the same two tests. Okay, now you certainly didn't need to watch me doing all these tests. And what we did here first was the standard 2.5-inch gallium arsenide lens, which for me is a go-to cutting lens. Now what I've done, as I explained a little bit earlier, was I've documented the hole size in the centre of the card, the evaporated section of the card, because hey, I'm going to try and use these figures to get the best cutting results. Now the halo around the outside is scorching, the sort of thing you might want for engraving. I'm not interested in these halo results. I'm more interested in just the centre hole evaporated results, which is where cutting has actually occurred. The standard 2.5-inch lens used this way round, which is the conventional way round, produces quite a sharp focus here, but that sharp focus is an intensity focus because it's where the most intense rays are damaging the material. And it happens at 59.5, which is 4 millimeters less than the manufacturer's specified focal point for this lens. And when I use it the wrong way round, with the meniscus side up, which is what I do all the time for my cutting, the actual hole has grown by 0.1, but it's over a much larger zone. We've got a wide range here where the beam is virtually the same size. 63.5 is the nominal value of this lens, so this does pass through the nominal focal point when used the wrong way round. We also tested this same lens with my very narrow 4mm beam, 30 watts, and here we get a completely different set of results. In both cases, look, we're 0.6, 0.6, 0.6, and here we're 0.3 and 0.4. So this is not as good at focusing the beam. But everybody keeps telling me that. But why? And that's part of the question what we're going to try and look at today. All the way from 55.5, we've only got a 0.2 variation over a range of about 11 or 12 millimeters there. Okay, and the same applies to this one. Look, we've got a very, very small range of change in that hole size over a very large distance. Are these two things related? The fact that this has got a short focal range and this has got a long focal range. In fact, this doesn't appear to be focusing. And the only difference is the difference in intensity profile that I'm putting through these two configurations. According to all the theorists that have been contacting me, they're all telling me the same story, which is the bigger the beam, the tighter you'll be able to focus. Well, that's a fact that I've known for many years. We've got a 4mm beam here, which can only focus down to 0.6. And yet we've got an 8mm beam which can focus down to 0.3 and 0.4. 1-0 to the theorists. Let's take a look at a few images of the holes that I've burnt so that you can associate my numbers with reality. Here's a microscope picture. You can clearly see all the fibre in the card. So this is the surface of the card. And what I've got in the background just here is a piece of green paper. If we raise the table up, you can even see the texture on the surface of my piece of paper there. So that's a piece of green paper in the background just to try and delineate the hole. So that one there is 59.5, which is the smallest possible hole. And then we start moving to 60.5 and the hole gets a bit bigger. And then 61.5 and then 62.5. And you'll notice that although the hole is getting bigger, the actual halo around the outside is getting a little bit tighter, a little bit better. And then we get to 63.5, which is the focal distance. And at that point there, the hole size and the halo virtually match. So you could say, well, that's the focal point, because most of the energy is passing through a single point. And if that's the definition of what a focal point is, then is about 0.7. In previous sessions, I'd found that I got what appeared to be a better focus with my very small beam when I used a compound lens. I've taken a 1-inch zinc selenide lens because the 1-inch zinc selenide has got the maximum curvature on the surface. Just seen what the gallium arsenide lens does. So let's modify its output by putting a different lens on top of it to make a compound. We've changed from 63.5 all the way down to 14 or 15.5. So we've dramatically reduced the focal length of this lens, whether we put a 4mm beam through it or an 8mm beam through it. Big beam in doesn't necessarily mean a compact focus. Look, we've got 0.4 and 0.4 from these two configurations with a big 8mm 70-watt beam. And yet with the 30-watt beam, we've got 0.3 and 0.2. That's just a point that I'm jokingly make at this moment in time. I'm not really being serious about that because there are much more interesting facts in this chart. We're definitely producing a focus, a distinct focus with these two configurations with an 8mm beam. What's happening with this 30mm beam? We're going from 0.6 down to 0.2 and back out to 0.6 or 0.7 over a wide range. And this one, well look, we're going from 0.6 to 0.3 and back out to 0.6 again over a very wide range. We're not getting a huge change in the focus diameter. Relatively speaking, these are quite stable, almost implying that we're not getting much of a focus with this configuration. We're definitely focusing because look, we've changed from 63.5 down to 15.5 on both of these situations. But we've got this rather strange benign characteristic of not very much change for a long distance. Okay, so we've just tested this lens combination to find out where its best focal distance is, and it seems to be that it's about 14.5. So we're going to use that dimension to try and do some cutting. We're going to try and cut a piece of 10mm thick MDF with this lens. And that's absolutely ridiculous because according to normal ray tracing, this is what the beam will do, and once it gets below this focal point here where we're going to pop it onto the material, its energy density, a term I don't like using, drops off dramatically. And so what we'll do before we start, we'll just take a look at what the footprint of that beam looks like as it exits the material. It's about 3mm diameter as it exits the material. And this at full 70 watts, but we're using 4mm a second. Even though that was where we supposedly set the focal point. And underneath, well, yeah, we've got more or less a cut, It's not a complete cut, but it's more or less a cut. Hang on, stop. What thickness is that cut as it comes out the bottom? I'd say it's about 0.1 or 0.2. Not 3 millimeters. Lens theory predicts something different. So I've always challenged people to answer the question, how is it possible with such a short focal length lens to produce a parallel cut? This is not trick photography, you saw me doing it. Okay, now I've changed to some 3mm HDF. We've set the gap to 4mm, which is 14.5, the nominal best focal distance we've found. We run that at 25mm a second. That's quite a nice thin line, and look over the back. Well, yeah, it's just about coming out. Look, oh yeah, we can pop it out very gently. So here we've got the small beam and 30 watts. Running this at 15mm a second. Well, it's a very nice cut. Let's look at the back. And again, it's just about come through very nicely. So if I just give it a gentle touch, look, it pops out. And that's at 15mm a second. Let's see if we can push it a little bit further. 16mm a second. I'd say that's just about cut through as a comparison with the other one, but of course it starts off as a much finer line, so it's going to finish up as a much finer line. But let's just push it. It's quite a snug fit in there, but it pops out very easily. I think that's really the limit at the moment, 16mm a second. Well, we're going to try this at 2mm a second. Again, you need to set this up to ideal focus, which is 4. The good news is the smoke is coming out the bottom. It has just about made it through, but that's 2mm a second. This is the burn on the 70-watt machine as the beam exits the bottom of the work. Let's compare that to see what it is on this machine. A lot of difference. So that beam is hardly expanding at all. So that's what the 70-watt machine looked like, and here's what the 30-watt beam looks like with its narrow beam. The centre part has hardly expanded at all. In fact, I'll tell you what I'll do. Let's just take the nozzle out. Let's just compare that with the naked beam. Well, when we take a look at that coming out of the lens, and that's a compound lens, remember, which has got a very, very, very short focal length of only about 14 or 15mm. That's the naked beam going into the lens. Hardly any difference in the central power diameter, is there? Which I think tends to hint very much at what I proposed last time. There is no focusing taking place right in the centre of the lens. That high power beam is passing right through the lens. In fact, in this instance, it's passing right through 2 lenses. But of course, both lenses have got the same property at the axis. Right over the back corner there, we have a completely different situation. So let's go and have a look at the burn over at the back corner. I mean, that compares size-wise with 70-watt machine, but of course we don't have the same intensity there because we've not really burnt a hole through there. Okay, so it's 30 watts. It's not going to do as much damage as the 70-watt machine, although we're now roughly at the same diameter. The question is that going to give us a better focusing because we've got a larger diameter beam? Let's go and test it over in that corner, shall we? So for comparison, we're looking at basically this column here against this column here. And here we've got roughly 0.6, 0.3, 0.6, a range. That's the size of our hole in the middle. In this case, we've gone from a 4mm beam up to probably a 6 or 7mm beam. And look, we've got worse results. Remember what I've been told? The bigger the beam, the tighter the focus. Well, here we've got virtually no focus and it's bigger than what it was here. Let's see what 4mm looks like, shall we? No hint of it coming through. Now, as I move away from the corner of the machine, the cut is getting sharper, the beam is getting smaller. I've just moved a little bit away from the back of the machine where the cut was rubbish. Let's give it a try here. And we've definitely got a burn taking place because we've got smoke coming out underneath. We can see the reflection of the flames underneath there. Now, I would say that that's quite a thick burn. So let's see if we can get the burn a little bit thinner by changing the focal point. So we'll go up to 5mm. As you can see, it's slightly thinner and less burnt. We haven't changed a lot underneath. Let's see if we can get it a little bit thinner. Let's go up to 6mm. Not a lot different, top or bottom. So when I do a penetration test between the two machines, I don't think there's any doubt in your mind which machine is which. These here are from the standard 8mm beam, my 70-watt machine. Now, these are the two compound lenses, and I changed the focal distance between these two because it looked as though just here there was a neck which indicated that my focal distance was a bit low and I really ought to raise it up. And as I raised it up, so I got rid of this neck and made the thinnest point onto the surface. And then I did much the same sort of thing with the other lens combination. I tested that at both focus depths. These are a 200 millisecond pulse. Now, normally the exposure time is so short that you won't be able to see this effect that's happening in here. And we'll talk about this effect later. But take a look at the difference between these and these. Now, you can compare the tops, they're roughly level, and you can compare the bottoms. This 30-watt machine on the left-hand side is penetrating deeper with both combinations of lens than the 70-watt machine. We appear to have more damage capability in this 30-watt very small diameter beam than we do in the 70-watt larger diameter beam. I mean, there's our 30-watt naked beam, and then we move to where the beam starts to grow here, and it grows from 3mm to about 6mm. Look what happens to the penetration. This is just confirming what we're finding. If we can keep the beam small, we get better penetration. Here, the beam is big to start with, and it's not penetrating as deeply, even though there's twice as much power there. These tests are not performing as I expected. In other words, the 70-watt machine still beats a sharp 30-watt machine. I normally assess a lens performance by virtue of the footprints it leaves in the sand. Some people are very adept at reading tea leaves, or pig's entrails, tarot cards, or the palm of your hand. I don't have those skills because they're looking into the future. Footprints in the sand are effectively looking into the past, and that's what I've got to do. I've got to try and analyse what this footprint actually means. By back engineering, I've got to predict what the light rays were doing from the damage that I see in this acrylic. I'm going to do some tests with the two compound lens configurations on both this machine and the other machine, and I'll show you the results. Now, you've just seen me doing these penetration tests with the various combinations of machines and compound lenses. Now, these are the two compound lenses on the 8mm, the big beam machine, the standard machine. Although it's a nice idea to try and show you a slow motion video, the problem with my video is it's 50 frames per second. Now that might sound quite a lot, but when you stop and think about it, that means one frame every 20 milliseconds. What I've done here is devised a test which enables us to see much more than the video can show us. 2, 4, 6, 8, 10, 12, 14, 16, all the way out to 30 milliseconds. So we can look at 2 millisecond intervals of beam growth and compare them with each other. This is a much better visual presentation of the way in which the beam grows. So let's just take a look at this picture and start at the beginning here at 2 milliseconds. Now after 2 milliseconds, look at this beam here. It's already developed as far as 2 millimeters deep, which is what these lines are, 2 millimeter intervals. Where's this one? It's hardly started. Well, it hasn't started at all. So at 4 milliseconds, we've got nearly 3 millimeters of damage. On this compound configuration, we've got a very large blob, the start of something. Now, because it is very large, it's not very deep. Whereas here, it's very small, so it's deep. I mean, this just again is confirming what we already have demonstrated before. The bigger the diameter, the less the penetration. So here, we're getting lots of penetration, and here, we're developing something. Now, all of a sudden, we stop developing this something here, this cone, because look, it remains constant all the way to the end here, up to 30 milliseconds now, more or less. Once that light intensity has done its damage, it appears that there's no more light intensity outside this cone to make this cone grow. So one has to assume that this is the path of the light coming into the focal point. And here we've reached a focal point, and now what happens beyond that focal point is we've got beam growth. We've got just the merest hint here, look, as I said, a very small amount of extra energy taking place and burning away. Instead of a sharp cone, we've got a very slight trumpet type cone here, but it's not changing very much at all. It's not really growing. It's a tube. Even with this 8 or 10 millimeter diameter 70 watt machine, we've got a central spike of intensity. You can't do damage to material unless there's light there to excite the molecules, to get them up above 200 degrees C and make them evaporate. What sort of light is getting down here to cause this damage? Look, it can only be light that's coming right down the central axis of the beam, passing through the lens, maybe being very, 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 very slightly focused nearly to infinity, so that we've got a column almost of energy which is trying to go straight down. Because remember, even on this standard 8 or 10 millimeter diameter beam, I've still got a very, very good Gaussian distribution which produces a very, very sharp beam. Even though this is a, relatively speaking, a big diameter beam, it's still got a very powerful centre which is trying to force energy right through that low amplification section at the centre of a lens, where the lens is trying to focus these somewhere towards infinity. That's why we've got these very long parallel pipes. This is a cutting lens, even though it's a compound with a very, very, very short focal distance. You can't cut with a lens that's that short unless somehow you're letting power right through the centre of the lens to produce this effect. So what you see on the screen there are those lens configurations. The smiley face, upside down gallium arsenide lenses on the bottom, and the standard compound that you would expect, which tends to produce zero aberration, is on the top. I've exaggerated the aberration on the bottom and tried to minimise the aberration with the top combination. Right, just bring that into focus. Now I've tried to arrange the surface so that it's pretty parallel across the top there. And what I want to do is just quickly zip across all of these, and you'll see that there is something happening just at the bottom of the screen. It's starting to develop a ballooning effect. Can you see that? It's like a neck that's starting to grow, but it's there all the way across in a consistent position for every one of them. And then as I start tracking down, you'll see how this ballooning effect is quite significant. And then it gets towards the bottom of the beam and it rapidly drops off. And then we get this strange effect just here, right at the bottom, this furry bit. Now I've often wondered what that furry bit is, but I think I've worked it out now. That's a heat affected zone. That's not actually cutting with light. That's cutting with hot gas. That's out of control cutting at the bottom. And that's what you get when you create beam drag. I think we demonstrated that in a previous session. About there somewhere is where the light is actually still agitating the molecules, heating them up and making them evaporate. Beyond that point, it's just hot gas that's causing the damage. Because look, it's no longer straight, it's getting out of control, it's veering off to the left. Light does not veer off to the left, it travels in a straight line. And if we leave the beam on long enough, it will straighten out. Now to explain how this ballooning is happening, I'm going to borrow a diagram from this wonderful document that I've referred you to many times before. First of all, we've got aberration, which causes these rays to effectively filter out. And what we're left with is this little bit down the centre here, which you can see is beginning to balloon out. But hang on, you're seeing this effect here with all these rays being of equal intensity. And we know that's not the case. These rays here in the centre are very, very powerful and the ones that are really creating most of the damage. So what's happening is we're getting a spike of power down the centre, which is creating a, if you like, a pipe of energy, a parallel pipe of energy, because they're so close to the beam axis. And you can see what effect that has here. Look, these are so close, they're having virtually no effect at all. They're running out somewhere close to infinity before they actually intersect and form a focus point. But in addition to that, what we're finding is we've got these rays which are close to the beam axis, which have still got lots and lots of power, and they're passing through this hole that we've created at the top of the acrylic, and they're going into the void that's below, and they have got enough power to still damage the edge of the hole that's been created by this parallel bit that's gone ahead of it. I can see this so clearly in my mind, how all these different intensity but very high intensity rays around the centre are causing this effect which is happening below the focal point. All this stuff here is very, very low intensity stuff which has not got enough intensity to damage the surface of the acrylic. This bit here, which is the cone that I was telling you about, has got enough. Look, you could almost see that that was the nominal focal point that I chose, and yet I pointed out that this cone here stopped working. And it stopped working because there was not sufficient power to damage any more material. And here is the cone from this other configuration. And you can see the cone all of a sudden stops, and it becomes virtually a parallel pipe all the way down to the bottom, where all of a sudden there, look, it starts to lose its light energy and it starts veering off in strange directions, because that's heat, projected heat energy. That's hot gas. And here's the configuration for those two lenses. We've got the upside down gallium arsenide on the top.
If we look at the penetration, there's little or no difference between them. Look at the size, there's virtually no difference in the diameter or the shape of them. It's almost as though the beam is passing right through the centre of this compound lens and not doing very much at all. We're certainly not getting any ballooning effect. We know that there's no beams crossing over and damaging inside here. We've just got straightforward, very, very close to the axis beams that are trying to find their way towards infinity to focus. So let's take a look at one of those in detail. And you can see that we've just got a hint there at the top of this conical bit where possibly the intensity focus is somewhere in the centre of the screen about now. And then from here onwards, it just becomes a parallel pipe. You know, there's just the merest hint of a little bit of ballooning there, but that's such a long way down, one has to wonder whether it could still be a crossover beam and a very slight effect of some power right close to the centre line. And then all of a sudden it drops off and we get this heating effect right at the bottom. If we scan down that beam after it's been cooking for 200 milliseconds, I mean, it's straight, and just towards the bottom we get our heating effect that we've seen before. Well, perhaps the answer lies in this comparison here. Here's the 8mm beam, and here's the 3 or 4mm beam. Now, if we look at the way in which this beam grows from 2, 4, 6, 8, 10 all the way up to 30 milliseconds, we can see that this is winning the race. This is the hare, and this is the tortoise. Now, the difference is here, if we look very carefully, if we plot a graph along here, you'll see that it's going up steadily, and then all of a sudden it starts to almost level off. So we've reached a bit of a transition point here where we're not going to grow very quickly. If we look at this one, it's still going up in virtually a straight line. At 200 milliseconds, where I did my comparison, this has won the race slowly. This one has stalled out. But of course, we're not cutting with pulses that are 200 milliseconds long. Right, just look over my shoulder at one of my little dodgy diagrams. We were able to cut through 10mm MDF with the big beam at 4mm a second. Now, let's just break that down. Let's assume that we had a cut of 0.2 wide. So every dot in a cut is 0.2. And let's assume that to simulate a cut, we look at dots that are 0.1 millimetre wide. In other words, there are 10 dots in a millimetre. Now, if we're running at 4mm a second, it means every millimetre is going to take a quarter of a second, i.e. 250 milliseconds. And if we're doing 10 dots per millimetre, 1 millimetre, 250 milliseconds, it means every dot is going to take roughly 25 milliseconds. Hang on to that number, and let's look back at this comparison here. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 milliseconds. Now in 25 or 26 milliseconds, this has gone 2, 4, 6, 8, maybe nearly 9 millimeters deep. At this point, the thin beam has not forced its way as quickly into the material. So the thin beam has the ability to carry on and produce a much deeper, smaller, thinner cut, given enough time. But we haven't got a lot of time. We're busy trying to cut. So the real enemy that we're faced with here is speed. Although this has the potential to cut, it doesn't have the ability to cut at the same speed as the more powerful beam. How disappointing is that? So, maybe the naysayers were actually right, but the reason I'm not going to win is for something that they have not considered, and that is the fact that I can't get this power to amplify through the centre of the lens. If I could get this very high intensity to amplify through the centre part of the lens, then yes, I would be able to push this. But as I said, there is just a part of the lens that really doesn't work. Focuses, but it doesn't amplify. But in every cloud, there is a silver lining. And here is that silver lining. That very, very small dot there at 2 milliseconds. And this explains why I was able to do some very good photo replication in one of my earlier sessions. You can't photo replicate with dots that look like this, but you can photo replicate with dots that look like this. So I think I've found myself an engraving monster and not a cutting monster as I originally set out to achieve. Now, is that success or is that failure? I really need this machine to be a high-speed engraving machine. So I suppose in those terms it's an accidental success, but my goal of proving that a thin beam will produce a faster cut has been a bit of a failure unless I can find a solution to this hare and tortoise problem. So thanks for your time and patience in this session. It's certainly been very enlightening for me and very enjoyable, but the problem is not fully solved yet, and I will continue working on it.